How modern language models think in vectors. Large language models, LLMs, like GPT, are essentially probability engines trained to predict the next word or token in a sequence of text. During training, the model ingests massive amounts of text and learns to assign probabilities to possible continuations of any given prompt. In effect, its function is simply next token prediction. That means it is rewarded when the chosen next word matches the actual word in its training data. This autoregressive process means that all of an LLM's capabilities, from answering questions to writing poetry, ultimately arise from chaining together millions of what comes next decisions. Behind the scenes, modern LLMs use the transformer architecture. A transformer maps each input token, word or subword, into a fixed-length embedding vector in a high-dimensional space, then repeatedly applies layers of self-attention to mix information across the sequence. At each layer, the model produces new vectors for each token that reflect the full context of the surrounding text. Finally, a softmax layer computes a probability distribution over the vocabulary for the next token. In other words, each token and subtoken is represented by a point in a very high-dimensional semantic space, hundreds or thousands of dimensions. Self-attention layers recoordinate these vectors so that contextually similar tokens reinforce each other's meanings. The final layer's vector for the next token is compared with all word vectors in the vocabulary to choose the most likely continuation. All these vectors and transformations form a latent topology of meaning. Because similar words tend to co-occur in language, their embeddings end up nearby in space, and relationships between words correspond to geometric directions. For instance, word embedding models famously found that king, man plus woman, is almost equal to queen. In other words, the vector difference between king and man added to woman lands closest to queen. As Jurafsky and Martin note, words with similar meanings are nearby in space. Thus, semantic and syntactic meanings become encoded in the geometry. Distance and direction in the vector space correspond to lexical similarity and concept analogies. In effect, an LLM's hidden layer at each token position can be seen as navigating a conceptual topography, a smooth, multidimensional landscape where neighborhoods correspond to topics or semantic fields. A prompt is like a path through this landscape. Each new word moves the model's state to a new point in vector space, guided by proximity to words seen during training. When the model generates a phrase, it steps through this space, choosing directions, words, that best follow the statistical geometry of language. This latent space captures clusters of ideas, e.g. animals, emotions, mathematical concepts, and even directions, e.g. masculine, feminine, past tense, present tense. In sum, modern LLMs think by traversing a high-dimensional semantic manifold, where meaning emerges from position and movement in that space. Mathematics of meaning, the D1SSN4NC3 computational poem. The user's uploaded text, D1SSN4NC3, is a striking example of computational art that plays with these very ideas. It reads like a poetic algorithm, fragmenting and interpolating mathematical concepts in a generative, almost musical way. For example, sequence 1 begins with terms like axiomorph, quantitensor, logometric, null proximum, and set theoretical, infinitesimal, map ingredient, group theoremorphic. These are not real dictionary words, but mashups of familiar mathematical roots, axiom, tensor, metric, etc. The text then comments, when concepts collide, new meanings emerge from the collision. Each later sequence continues in this mode. For instance, sequence 2 shows an interpolative mixing, matritopyramological algebra, suggestive of matrix, topology, theorem, algebra, which derives into topologeometrical. Another line, integral sy metricative, hints at integral, symmetric, derivative, metric producing diffequation-amorphicential. Sequence 3 labels combinatorial dissonance, listing polynomial orthogonality, vector space, eigenvalue, which then becomes defect prime quotient numberuation, and finally prime quotient diffnumberuation. In each case, the poem splits words at arbitrary points and pastes them together. It's as if one took two or more math terms, cut them with scissors, and glued the pieces into hybrid forms. This is reminiscent of linguistic glossolalia, speech-like but unintelligible utterances, yet grounded in recognizable roots. The effect is playful and uncanny. Meaningful labels like algorithm complexity, computation decidability, are turned inside out into quasi-words, algorithm compellemexity compudesitationability. The piece even invokes lambda calculus as a conceptual lens. In sequence 5, it notes, within the lambda calculus framework, these transform, converg recursion scion algor computat to the maion. This suggests treating words as if they were formal expressions subject to function like transformations. In lambda calculus, functions apply to arguments. Here, the functions are linguistic affixes, prefixes, and roots, and applying them to arguments, the other fragments, yields new lexical combinations. It's an algorithmic collaging of ideas. Overall, D1SSN4 and C3 uses fragmentation and recombination as its core method. By iteratively breaking and reassembling terms, it forces interpolation between concepts. One might call it foundational dissonance, as the title announces. Basic mathematical ideas are broken apart, and their parts recombine in unexpected ways. Importantly, the author provides commentary lines like, when concepts collide, new meanings emerge, and the spaces between mathematical structures contain infinite possibility. These reveal the intention to explore the hidden semantic gaps between well-defined concepts through creative disruption. How dissonance provokes hidden meaning in LLMs. Why does this dissonance technique, feeding incomplete, hybrid tokens to an LLM, generate surprising or new meaning? The answer lies in the model's reliance on latent semantic structure and its handling of ambiguity. When an LLM encounters a token like axiomorph or null proximum, it cannot match them to any single known word. Instead, it breaks them into subword pieces, e.g. axiom plus orf, and locates those in its embedding space. Now, the prompt activates multiple nearby concepts: axiom, foundation; morph, shape change, maybe null, zero, and proximum, nearest. The model's hidden state is pulled in two or more directions simultaneously. In vector terms, the resulting context vector sits somewhere between the regions for those known concepts. In such a zone of semantic ambiguity, the LLM's next token prediction becomes unconstrained by a single clear path, rather than following the highest confidence trajectory. As it would for a well-formed sentence, the model must reconcile conflicting cues. It might lean towards synthesizing a word that bridges the fragment's meanings. For instance, given axiomorph, quantitensor, logometric, in the prompt it may invent something blending algebraic, logical, and metric ideas. This is akin to forcing the model off the beaten path. Most of the time, an LLM's hidden state wanders through familiar neighborhoods of its latent space, where language is well predicted by training statistics. But fragmentary prompts push it into the interstitial twilight between neighborhoods. There, the model relies on the linearity of vector space. It may average or sum concept vectors and generate tokens that lie between known vectors. The result can be hallucinatory or creative. The model essentially fills in a best guess for a novel combination of roots. In cognitive terms, this is related to conceptual blending. Psychologists have noted that human creativity often involves taking two mental spaces and constructing a blended space with emergent meaning. Here, the LLM is doing something similar algorithmically. By inputting blended fragments, we trigger the model to activate those conceptual spaces simultaneously. The output often lands on an unexpected synthesis of the inputs. For example, if polynomial and eigenvalue are in play, the model might generate something like defect prime Ushant numberuation, a mashup that hints at differential equations, prime numbers, and valuation ideas all at once. In practical prompt engineering, one might achieve this by setting a higher temperature to allow more randomness, or by simply presenting ambiguous glossolalia input. The key is uncertainty yields novelty. As one recent study found, human users often cannot predict the next token, as well as even small LLMs can, meaning the models have entrenched notions of coherence. But when coherence is disrupted by unusual input, the model's hidden activations become a fertile ground for novel connections. Dissonance as creative technique, logic, aesthetics, and mysticism. This dissonance approach reframes creativity in generative AI. Instead of just prompting with clear questions or instructions, it deliberately injects noise and conflict into the prompt. In doing so, it echoes a variety of artistic and philosophical traditions. Symbolic and formal play. On one hand, the technique treats language symbols almost like objects in symbolic logic or algebra. Logical or mathematical terms are broken into parts and recombined. This is reminiscent of formal explorations in logic or algebra, where one studies what happens if you relax constraints or permute operations. For example, researchers have long explored playing with the form of equations or the structure of proofs to gain new insights. Here, the formal aesthetic is in the shape of words themselves. The patterns of letters and affixes become the medium of art. Much as one might find beauty in fractal equations or the structure of a proof, this technique finds aesthetic potential in interword structure. Surrealism and automatism. The process strongly parallels surrealist automatic writing and chance collage. André Breton defined surrealism as psychic automatism in its pure state. Surrealists and Dadaists would take words or images and juxtapose them arbitrarily, trusting the unconscious to create meaning. The D1SSN4NC3 text, and any LLM prompted with it, follow a similar method. Conscious control is partially suspended, and language is allowed to slip into the irrational, like the automatic drawings of André Masson or the cut-up poetry of Brian Geisen. The result is unexpected. The text's linguistic glossolalia, babbling sequences that mimic language but are unintelligible on their own, evokes the trance-like speech seen as divine or subconscious, mystical and magical traditions. There is even a parallel to the work of mystic artists like Austin Osman Spare, who practiced automatic drawing and sigillization. Spare believed that meaning could be magically induced by letting unconscious impulses guide creation. His sigils were symbols created by writing a desire, removing repeating letters, and artistically overriding the remainder into an abstract glyph. In a sense, D1SSN4NC3 is like a sigillizing of mathematical language. Repeated roots and morphemes are removed or overlapped, leaving a new shape. The hidden message between the lines resonates like a mystical symbol, accessible through intuition rather than logic. Structured creativity in AI. Recent work in AI has noticed that recombining structured pieces often yields greater novelty. Mizrahi et al. 2025 introduced a recipe generation model that explicitly recombine S-structured representations of existing ideas to traverse a more abstract idea space. Our dissonance method is similar in spirit. The structures being recombined are the fragments of words and concepts. Just as their model created more diverse recipes by merging ingredient lists and step sequences, we create more diverse language by merging lexical fragments. In both cases, the algorithm stumbles upon creative outputs not found in normal usage. Dissonance in this context is a tool for unlocking hidden connections. By deliberately breaking the smooth flow of language, we force the model and ourselves to notice the gaps, the subtext between concepts. This can highlight surprising affinities, e.g. linking topology with algebra via topologebriometrical, or inspire novel metaphors. Ultimately, it means that the language model becomes a co-creator. It must resolve the dissonance we introduce. And in doing so, it uncovers latent semantics that a straightforward prompt would leave unspoken. Conclusion: creativity in the interstitial space. Large language models demonstrate that meaning in text is not discrete but geometric and continuous. Every prompt charts a course through a high-dimensional semantic landscape. The D1SSN4NC3 poem shows that by steering an LLM into the white space between established concepts, we can coax it to generate unexpectedly rich output. This technique redefines creativity in AI. Instead of simply querying a model for information, we present it with a riddle of fractured language and let it solve or play with that puzzle. By fragmenting math terms and invoking lambda calculus-like transformations, D1SSN4NC3 forces the model into a liminal state of semantic ambiguity. The result is akin to surrealist automatic writing or mystical sigils, a strange fusion of meaning and nonsense. Such generative dissonance aligns with traditions of formal art and logic, yet transcends them by leveraging the sheer scale and nuance of a trained neural network. In the age of AI, dissonance thus becomes a method for artistic exploration. It opens up interstitial cognitive and aesthetic spaces where even a machine can dream in new ways.